Hey, everybody. So I'm not sure if everyone was following the live stream, but they just finished, and I see Gino just arrived. So I'm going to wait another minute or so just to give everybody a minute to get in here in case they're switching. But hope everyone's doing well. This is interesting. This is the first time I've done an all virtual international conference. So I think we've got people who are, I suspect, like I see Greg, who I know a little bit, and I think he's probably on California time, so it's probably the middle of the night for him. And I think we've got people in all time zones. I think it's evening for some of us, I'm guessing. So.
I'm also in California time, so
yeah.
Just interested, Greg. Did you go with the staying up late or the waking up early strategy?
I slept before this, so it is the middle of the night. I will sleep afterwards also.
It's pretty smart.
Okay, so I think we'll go ahead and get started. Well, anyway, yeah, thanks everyone for making this work whatever time it may be for you. And as is somewhat expected, I think in the actual workshop, we're mostly going to have the presenters, but we will be recording this. Well, it is being recorded currently, and I plan to post it, so people will maybe seeing your presentations. But yeah, I'd like to keep it, since we have a small group, it's a good opportunity to just kind of chat with each other and keep it casual to the extent that we can. So anyway, each presenter can do it the way they would like. I'll go ahead and get us started. Okay, well, welcome everyone. I'm Ryan Gardner. I'm from the Johns Hopkins University Applied Physics Laboratory. You can see there are a number of people involved in organizing the competition. Gino, who's also on, and I are the people here in the workshop today. And we're both from the Johns Hopkins Applied Physics Laboratory. That's the main organization organizing this, although there are a number of them. And so here's our agenda for the workshop. I'm going to give a quick intro. I assume everyone saw or I imagine most people saw the overview video. So I don't want to be too duplicative of that, but I'm going to just give a really quick recap of the game in case anyone missed it. And then mostly I want to just go into a little bit more depth on some of the research challenges in the game. And then Gino is going to talk about the tournament results. And then after that, we're going to hear from the various algorithm designers. These are, for the most part, in no particular order. We just kind of wanted to keep some variety. Although you'll see Fianchetto, the champion for this tournament, is going first. So, like I said, for me, if people have questions, I'd encourage you to just, we can potentially keep this interactive. If you've got a question and feel like interrupting, go for it. Other speakers, if you'd rather wait for questions until the end, just let everybody know. But our presentations will be approximately 10 minutes each, but we're not going to we don't need to stick to a real rigorous schedule here. Okay, so for anyone who missed it, I would like to give a quick recap of the game. Reconnaissance blind chess was created as a testbed for AI under uncertainty at the Johns Hopkins University Applied Physics Laboratory. It's like chess, the pieces move like chess, but each player can't directly see where their opponent's pieces are. But rather, they do get to privately use what we usually refer to as a sense action. They get to select a 3x3 square of the board each turn, and they do get to observe what's in that 3x3 square. And the point is to abstract challenging aspects of real life scenarios, particularly those with uncertainty and with no common knowledge or no public knowledge. To give a few more details than we're in the overview, I'll just mention if you're trying to imagine this game and you're wondering about a few things, there's no notion of check because you don't know if you're in check. So there's also no notion of mate. You win by capturing the king. Similarly, you could castle through check because there's no notion of check. You do get notified of captures if your pieces are captured. An illegal pawn move in general results in no movement. One exception to this is if you try to move a pawn up 2 spaces on the first move and there's something in the way, but it can move up 1 space, it will move up 1 space. Sliding pieces, such as rook, if you try to move that rook across the board, but it hits an opponent piece on the way, it'll stop and capture that piece that it hit. And there's also a pass move. So as I mentioned, the main thing I would like to hit on with this brief presentation are the research challenges in reconnaissance blind chess. The one that is by far of most interest, in my opinion, is the imperfect information and little public knowledge. And this makes it very difficult to decompose the game into subgames in a sound way or to conduct search. Also talk about abstracting the game and neural learning. So let me begin by talking about search. When we think about search, first let me put this in the context of a game of perfect information. First of all, when we have a game of perfect information, like I'll usually relate back to just regular chess. The optimal strategy in that game is a pure strategy. Potentially, there could be several strategies that are equally good, but there is an optimal pure strategy. So every time you're in a particular situation, you could, for example, move your rook to this space. In general, with imperfect information, this is not true. If you imagine an easy way to think about this is think about rock, paper, scissors. Certainly a pure strategy in rock, paper, scissors is not good. The optimal strategy in general is probabilistic. And if we think about search in a game like chess, if I'm 10 moves into the game and I look down at that board, all I need to do, I can think about how all the pieces move forward from that point in the game, and I don't care how they got there. And that makes so we can just look at that subtree going forward from that point. And this idea has been central to all chess AI, really from the beginning of chess AI. And it makes a really big difference. However, with imperfect information, in general, you cannot do this. You have to analyze the entire game, even when you've worked your way into the game. So in other words, those unreachable states still affect relevant probabilities in the game. And that's a very big difference. Another major difference between search in perfect versus imperfect information settings is in a perfect information setting, a state, as we usually think about it, and of course there are many ways you could define this, but typically, as we usually think about it, a state has a well-defined value. But depending on how it's defined, this is not the case in general with imperfect information settings. So consider the example of if we're playing poker and we're in the state of, I just bet all my chips with a hand, a bad hand, say a 6 of hearts and 2 of clubs, and there's $1,000 in the pot. If I bet like this rarely, then this has some positive state value for me because opponents may fold. Well, it may not, I guess, shouldn't say, anyway, there's some non-zero value. If I bet like this all the time, however, if I'm constantly bluffing, then the opponents will call me all the time, and the value of this state is much less. So in other words, the value of a state is dependent on my past on the strategy. So these summarize two core differences very briefly. So in spite of these challenges, there have been a number of approaches presented for conducting search in a sound way with imperfect information games. I've got one of these illustrated here. One approach, which is frequently referred to as continual resolving or a nested subgame solving, allows you to restrict the breadth of a search by essentially saving off critical information as you work your way down the tree. And then you can actually just look at some important information that was saved during the analysis of these subtrees off to the side. And you can actually restrict the breadth of your search. But the critical thing here is that the first step of doing this is you have to decompose the game into, you have to think about the game in terms of public states, and you decompose the game along public states. And this is really important because that public knowledge, this is essential because the optimal strategy is dependent on, my optimal strategy is dependent on my opponent's beliefs and their beliefs of my beliefs and so forth. And that's why this is essential to decompose along public lines. And what I mean by that, when I say decompose along public lines, is each of these states is defined by some common set of public information. And that's information that's available to all players. So for example, if we're playing poker, those 3 cards that are on the table that everyone can see, or if we're talking about Texas Hold'em and all the bets, that information is public to everyone, and that would define one of these states. The problem here is that with reconnaissance blind chess, in general, you do not know what your opponent knows because you don't know where they sensed. And so the public subgame is very simple. It's a little more complex. I've exaggerated a bit by approximating with one state, but there is not much, there's not a significantly large public game, or in other words, there's little common knowledge. There are also approaches to limiting search depth, but these have challenges as well as a result of this lack of common knowledge. And these, as I was mentioning, are really some of the core research challenges in reconnaissance blind chess. Also briefly talk about reducing the game with abstraction. One of the things that was done with poker and the superhuman poker bot Libratus is they reduced the size of the game by abstracting it. And there's 2 ways we can think about abstracting things. We can reduce the state space. So in other words, take a bunch of states that are similar and just map them with one abstract state. So we could call all king high flushes the king high flush state, for example. And we can abstract actions as well. So call a bet of 1,002 chips the same as a bet of 1,000 chips. But with reconnaissance blind chess, there's no obvious abstraction that won't significantly lose fidelity of the game. The last thing I'll mention are challenges in using deep reinforcement learning. So there's some very interesting research that presents sound ways. You could use deep reinforcement learning to get a theoretically optimal solution to reconnaissance blind chess. One of these I'll mention is deep counterfactual regret minimization, or deep CFR. However, practically architecting and training the neural nets to do this is challenging because the history of the game can be relatively long and complex. And so a way of actually doing this in a practical sense is still an open question. Okay, and so I'm going to wrap up there. I'd just like to conclude by welcoming and encouraging everyone to join our research community. we're hoping to make this an annual competition until we feel that the research challenges have been addressed. This game was also, I've got on here, it was part of the Hidden Information Games competition. They had a great, really interesting, ambitious goal of, in short, enforcing that the solutions were extremely general to their competition. And I understand actually that this was recently canceled, so I'm not sure where it's going to go, but I think we should follow up with that because it seemed like a very interesting competition. And Reconnaissance Blind Chess was one of 3 games. But regardless, we're hoping to make this an annual NeurIPS competition. You can play as a human on our website, and we also have an Android application coming with iOS to follow where people can play. So does anyone have any questions before I hand it off to Gino, who will talk about the tournament results? Okay. Well, next I'll hand it off to Gino Parada. As I mentioned in the overview video, Gino actually won. He was the co-author, along with Robert Parada, of the bot that won in our 2019 NeurIPS competition. And then he joined the Johns Hopkins University Applied Physics Laboratory, and you've got him to thank for actually making this happen.
Right. Thanks, Ryan. Share here. So well, I want to take just a minute in between these two portions of the intro presentation, just to say hi and welcome to everybody. I've been kind of peeking down the participant roster here during Ryan's talk, and I see we've got a lot of authors of the agents in this tournament. I'm looking forward to hearing from everybody and to the discussion that comes with all of these presentations. Largely, I'll aim kind of what I talk about to you all, but we are recording this for for the information of interested parties later. So for some things that might be obvious to people who just spent a couple of months thinking about this problem, we'll still go over. Right, so I get to talk about the results. If you did get to watch our pre-recorded intro video just before this workshop, you'll have seen some of this already. But we had to record that well in advance, so actually like immediately following the tournament. I've had a little bit more time to tease out some of the more interesting and entertaining bits of information from the tournament results. So let's see. There we go. Right, so just to reiterate, we had a round robin tournament between 18 agents. Each played each opponent 60 total times. The games were limited to 15 minutes per player, and bots played 4 games simultaneously so that we could complete all 9,180 games in what was targeted to be a week, but took 3 days, each game taking on average about half of the total allotted time. And you can see the full roster here rated on Bayesian Elo. And congratulations to the team behind Fianchetto, who not just won, but won resoundingly. If I rush through this presentation, it's just because I'm really looking forward to hearing from them. In these 9,180 games, 1.3 million unique information sets were reached. That is the perspective on the game from each player separately. Of these games, most ended the intended way, with the losing player's king being captured. About 7% of games ended when a player ran out of time, and about 14% of games never properly started due to internet connection issues or code bugs or whatever the case is on agents' local machines. Of the non-forfeit games, the win rate was very evenly split across the sides of the board, the white pieces and black pieces winning 51% and 49% of games. A couple of interesting things to pick out of this histogram of game length in full turn count. For instance, the average game in this tournament was 20 turns long. And we can see there's kind of peaks in the histogram at 4 and 14 turns, which I think corresponds to very aggressive and the not very aggressive strategies. There is, of course, an extremely long tail on turn count. In fact, I've truncated the x-axis here, well below the maximum game length, which is over 4,000 turns. Although almost every single one of those is trivial nonsense, with 2 of the baseline bots getting stuck passing back and forth with no actions. I've color-coded this histogram based on the end game reason. And I think it's interesting to note that games in which an agent ran out of time are not heavily biased towards games with a large number of turns. It was possible for an agent to get stuck thinking, or for whatever reason they ran out of time very early, as early as what appears to be turn 2 here, although that could be a bug misrepresented here. I think it's interesting to kind of look at the opening moves across the entire tournament in comparison to traditional chess and to intuition about reconnaissance blind chess. We bring up a histogram here of, or really, I guess, bar chart here of the most popular opening moves for white, color-coded by the fraction of games that went on to win from that move. We see, in fact, that the top 3 moves are exactly the same in the same order as chess. However, the most popular opening move, E2 to E4, has a significantly above average win rate, while the second most popular move, D2 to D4, has a substantially below average win rate. And as we see, even though the agents in this tournament selected these moves most commonly, it might be the case going forward that some lessons learned from this will reshuffle this order significantly. Also of note, the 7th most popular move was to not move at all on the opening turn. That didn't result in a particularly high win rate, but is an interesting strategy. And let me see, 5th most popular move, C2 to C4, has an extraordinarily high win rate. I think that corresponds to C2 to C4 really only being used in extremely aggressive openings, where the intended path is then to move the queen into the A file and immediately go for capturing the opponent's king, which appears to have worked quite a lot of the time. The opening choice of sense location for the black pieces generally reflects the correct assumption that the opening move for white will be the same as in traditional chess. The win rates across these are not so obviously reflective of later game meaning, but it is noteworthy that the highest win rates, D3 and C2, are both options which would identify whether the opponent had used that C2 to C4 aggressive opening. So I think a lot of these win rates in these 2 bar charts are particularly revealing aggressive attacks and the ability to respond to that. At the other end of the game, there's a couple of interesting final turn statistics to assess. For instance, what's the material advantage of the winning player? All of this is this histogram of advantage in pawns using the traditional 1, 3, 3, 5, 9 scores for the chess pieces. And the advantage is from the winning player's perspective. So regardless of which color pieces they were playing, we see that generally having more pieces than your opponent tends to lead to winning. And that's obviously not a surprise. Potentially more surprising that the most common material advantage for the winner is 0. Very frequently, games in reconnaissance blind chess are even. And there's a substantial tail off to the left here, in which the player who won did so from a significant disadvantage in material, potentially on the back of better information management, or just better strategy in the face of uncertainty. In an attempt to kind of roll out this uncertainty and highlight the importance of that other aspect of this game, I have traced all of the games from each player's perspective to count the number of possible board states that could be true given the information available so far in the game. And this is a histogram here also colored by win rate on the log scale. So we see all the way on the left is when the player had perfect information on the final turn of the game. And then all the way out on the right is an open-ended bin for everything 1 million or above states. And what I think is particularly interesting here is that apart from those extremes, there's not a lot of correlation between the uncertainty and the number of board states and the win rate. It's all as close to 50-50, enough to be lost in the noise. Now, if you have perfect information, it appears above average chance of winning. And if you have above 1 million possibilities, it's a below average chance of winning. But really in the mix here, most agents seem to be able to manage uncertainty within that whole range. So these statistics kind of beg us to peek at the extremes. And so we can see that my own agent has the dubious honor of losing from the farthest ahead. W. Bernard 5 managed a very good sneaky attack when my agent took a gamble that it wasn't in check from nearly 30 pawn advantage and lost. And it's easy to think that maybe this is just information management. Did W. Bernard 5 do a lot better at keeping the number of states down? But both of the agents for the final few turns of this game kept their number of possibilities in the range between 50 and 100. So it's not fully explained by the quantity of uncertainty. It seems more in the strategy side that W. Bernard 5 was able to come up with a strategy or identify the right time to do this particular attack. And for those of you who have been distracted by this histogram wondering how in the world is a 60 pawn advantage even possible, here's the incredible end game state of this otherwise kind of uninteresting game between two baselines. The let's see, the Bayes Elo rating used for this tournament gives not only an estimate for every player, but a confidence interval. So here we can see at the end of all 30 rounds, the estimate and 95% confidence interval for all players. It only took about 20 rounds to identify outside of this confidence interval that Fianchetto was a clear best, which is really impressive. Down the ranks, some bots are much closer together, and it may not have been within the ability of this tournament at all, regardless of how many more rounds or how many more days we played, to differentiate some of these very close competitors. And in fact, for kind of forward-looking algorithm evaluation, not just tournament standing, but assessing the strength of these, we can replay that rating without the forfeit games and see that a couple of these kind of internet connection issue caused losses can be wiped away. And in particular, I just want to highlight that the agent Kevin fought an incredibly close race for second place. Yeah, I see in the chat here, you can see where a couple of the agents disconnected. And yeah, I think for us, the bot authors and anyone, the future bot authors, kind of this re-evaluation without the forfeit games is where we want to focus our assessment, comparing strategies. Now, a couple of the following plots I have up here for the sake of the replay. Those of you who really want to get into some of these numbers, we'll have them available. I'll just highlight a couple of quick things on this cross table. This is the number of wins that each player in the row achieved against each player in the column. And as I noted previously, the overall win rate is generally a good predictor of the individual matchups win rate. The only real exceptions are that somewhat unexplainably, I'm not sure which, Frampt seems well above proportional in, let me get this right, in wins against W. Bernard 5 and losses against attacker. And I'm not sure why that would be, but those are the kind of standout cells along this cross table. Everyone else seems to fall pretty much proportional to their overall win rate. This again will be a little bit of a repetition from the pre-recorded message if you saw that, but in addition to playing out all of those sensing uncertainty management for the final state of the game, we can look at that kind of median uncertainty management across the whole, every phase of every game, and see in general that keeping the number of possible states low or manageable is clearly critical to success, in that the top fraction of the roster, the top performers do keep that number low and the bottom performers don't. There's clearly more to the story, as there's not enough difference in this statistic to differentiate the top performers. And I think expanding this into a cross table does highlight some really interesting things, like Callum Canavan being able to drive up uncertainties substantially more than any other opponent for all players. And I know that they were able to do that by frequently not moving at all, which doesn't convert into a high win rate for them in this tournament, but I think is a strategy that could be adopted or improved kind of in a lot of places for potentially any of these higher agents. And then to move into comparison for moves, we looked at agreement with a stockfish top 3 move choices given perfect information. And again, see that generally moves that are strong in chess are strong in reconnaissance blind chess, but that again, there are substantial areas where this is different, and particularly for this cross table, I'll have to leave it to you all to tease out some takeaways from opponent perspectives. But I can highlight some interesting counterexamples, particularly, as I mentioned before, just these sneak attacks. WBNR5 managed 94 games to capture their opponent's king by turn 3, which is just as early as it's possible to do so. I think that's incredible, and certainly means that the D7, D5 opening for Black, strong in traditional chess, very weak in reconnaissance blind chess. And so assessing your own uncertainty and your opponent's ability to exploit that means that this game is significantly different. Later in the game, the same case applies, but it's much harder to both to find examples and for an agent to successfully do so. Here's one example in which the counterfactual regret minimization algorithm Marmot found a sneak attack and assessed appropriately this time that Strangefish 2 would be vulnerable to such an attack. Generally, it's a little too difficult for these uncertainty-aware algorithms to compute in reconnaissance blind chess the moments at which their opponents have high uncertainty. But theoretically, it is possible, and occasionally it does work out. So I think improving this ability is a kind of a key open area to maybe the next breakthrough for RBC algorithms. All right, I dragged on a little bit there, but we can definitely open for a couple of questions on the results before we move into the algorithm overviews, if anybody has something they want me to revisit from those tournament results.
I don't have any question right now, but I just want to say that was really cool. Yeah, those statistics that you pulled up were really awesome. So thanks.
I appreciate it. I'm happy to hear it. Well, I am as eager as anyone to hand this over and hear from presenters, the authors of Fianchetto. So given that we'll have the continued opportunity to kind of discuss a tournament and the game in general over the course of this workshop, I won't make you guys think of a question right now. I am going to find here it is. I've stopped screen sharing, and I will pass that over to whichever of the authors is going to screen share and present. The floor is yours. Welcome, and thanks for presenting.
Hi everyone, I'm going to present my screen. So I hope everyone can see my screen.
Yep.
Okay. So hello everyone, my name is Mohammad Tawfiq. I'm an undergraduate student from Indian Institute of Technology, Bombay. I will now be presenting the algorithm used by our bot Fianchetto that won the NeurIPS 2021 competition on reconnaissance blind chess. So I will first briefly go over the baseline code used by our algorithm, which we took from the publicly available 2019 version of Strangefish. Then I'll outline the approach we took and all the improvements we added. After that, I'll go through the evaluation of all the changes, which will be followed by a brief description of some of the work that can be done on a bot in future. So going over the code for Strangefish. So this is the score function for Strangefish. It takes a single board as input and provides the score for each possible move on this board by simulating each move and then passing it the resulting boards to the Stockfish chess engine, along with some additional heuristics. The score function is used for evaluation in both the sensing and moving strategies of Strangefish. Now coming to the move action strategy, Strangefish takes every board in the board set and passes it to the score function to obtain the score for all moves on this board. This is done for every board, and the move which has the highest cumulative score across all board is selected for playing. In the sensing strategy, Strangefish first expands the board set by simulating all possible opponents' move, and then it obtains several reduced board sets by simulating the sense results. Now each board set is passed through an evaluation function that combines the expected board set reduction and the change in move score through sensing to provide the best sensing square. So this was an overview of the Strangefish code. Now we'll go through our approach. So now we had found out about the competition on RBC in August of this year. Hence, taking Strangefish 2019 as a baseline, we decided to tackle the highly critical issues we found in it. Therefore, we added the following major changes to our baseline to increase its performance. The very first one of them is the change that we made was to replace the Stockfish engine with the open source neural network based engine called LC0. So LC0 takes a board as input and passes it to the policy network, giving a probability distribution over all the possible moves in the board. Hence, unlike the Stockfish engine, which requires as many calls to it as the number of moves, LC0 evaluates all the possible moves in a single call. In the table below, we compare Stockfish with a LC0 network of similar rating. We can see that even though the time for a single call of LC0 is higher compared to the Stockfish engine, the number of board evaluations per second of both the engines is roughly in the same order of magnitude without batching. However, since LC0 can run on a GPU, it can evaluate a batch of chessboards in parallel. Therefore, with a batch size of 1024 on a 1 GB GPU, a single call to LC0 can evaluate a much higher number of boards than Stockfish. So this was the first change that we added. The second one is that the second change that we made was with regards to maintaining the board belief set. So Strangefish sets belief statically without utilizing the belief set at previous time step. That is, if we assume that the current state is S dash, the previous belief is B, and the observation is Z, then the updated belief for Strangefish is directly obtained using the Stockfish engine and applying a sigmoid function over it. Now, since this update equation doesn't use the previous belief in the right-hand side, it is independent of the previous belief and hence poses a lot of issues. For example, the static belief evaluation can often give considerable weight to boards with negligible previous belief that are very unlikely to follow from the previous set of boards. So this is like one issue that we thought was necessary to fix. And so to mitigate this problem, we model the game of RBC with a POM-DP, where the opponent follows a fixed policy and the belief is updated using the Bayes rule. So therefore, in this particular equation, this again state S dash is the updated state, current state, B is the previous belief, Z is the observation. And so probability of S dash given B and Z is the updated belief at the current time step. We can expand that to express that in terms of the opponent's move probability and the belief at the previous time step, which is probability of previous state S given the belief B. Now, this particular term in the middle can further be expanded using the Bayes rule, which gives us the probability of the observation given the state and probability of the new state given the previous state, which can be obtained from chess RBC rules. So in this particular update, we use the previous belief and the opponent's move probability to update our belief at every time step. Now, here a major issue is that how can we estimate the opponent's actions since we don't know how the opponent is generally going to play. So for that, we estimate this opponent's move probability using the LC0 engine with some RBC specific modifications, which we are going to explain in the next sections. So this is the second change. Now coming to the third RBC specific change, as I said, we modify the output policy of LC0 with some RBC specific changes. So here we provide incentive vectors for some particular move, incentive vectors in which we reward particular moves and we provide incentive to them. So for that, we pass the state S through the LC0 network and get its output from the last layer and add to that the incentive vector and apply the softmax function over it to get the probabilities. Now, the first particular heuristic was the piecewise dynamic sneak reward. As you can see in the following figure, this particular bishop move was played to attack the opponent's king. Now, if this particular move is not sensed, then we can directly capture the opponent's king in a single move. So such moves are given a high incentive. But similarly, a move that is shown on the right is also a good sneak move, but it's not as good as the left one, since if the opponent senses the particular bishop move, then we are in a risk of losing this particular piece. Therefore, we provide a lower incentive for such high risk moves. The second thing we did was incentivizing pawn attacks. In general, a pawn attack in RBC on expectation is a good move, because if the opponent doesn't sense the pawn move, for example, in this particular figure, pawn from H2 to H4, if the opponent doesn't sense this region, then white can simply win this bishop directly. But if they sense, they'll have to just bring that bishop back. Now, again on the right, if we attack this particular bishop and black doesn't sense this region, then we can win this bishop. But on the other hand, black can still sense the region and capture the square. So we again provide a smaller incentive for this, but this still works out in the end, because since losing out a pawn is not as bad as winning a piece, so it works in expectation. And for the third RBC specific change, let's go through this demonstration. Here, the black queen has given a check to white king from the square B6. So here, if white senses this particular check, then the possible moves it has is to move the king away or play the pawn from C5 to C4, C6. So now, if let's consider the particular move of C4 to C5, here, if the most probable way for black to play on is sense the opponent's king. So in most cases, they'll sense this particular region and see that the king has not moved since this particular pawn move was played. As they might not be aware of this move, their most probable strategy would be to try to capture this king. And if they do so, in this particular case, they'll lose out on the queen since this particular pawn move was played. And hence white will instantly win this queen. So again, we incentivize such moves that are, in case of a check, we incentivize such moves that are far away from the king, and that can also prevent the check, just like the pawn move. So these are some RBC specific heuristics that we added on top of LC0. Now the fourth particular major change that we made was to control the board set size. So firstly, we added a dynamically weighted uniform distribution to opponents' move probabilities obtained from LC0 to unbias the chess policy from LC0. Yeah. And secondly, we give more importance to expected board set reduction score in the sensing strategy as the board set size increases more. So as you can see in this diagram, we have plotted the average board set size maintained against each of the bots. And as you can see from the orange bar of V4 is significantly lower than the blue bar of V3 for all the bots. So this particular change especially helped us in maintaining a lower board set size. Finally, I'll go through the evaluation that we did for each of these versions. So here's the table for all the different versions. And so we formally tested out these versions against the organizers bot that were always available on the RBC server after the tournament was finished. So here we can observe that V1 does not play particularly well against Rangefish 2, as V1 loses more often than wins. So the switch from Stockfish to LC0 network, although improved the efficiency, does not directly result in improving the performance of a bot. Whereas V2, on the other hand, shows a considerable improvement against almost every other bot, including Strangefish 2. Now, including the RBC specific changes in V3, although seems to be reducing the performance slightly, but it eventually helps in a better gameplay and improved performance when combined with the changes from V4, which is able to beat every other bot consistently. And here's the win-loss table that's already explained from the tournament, so I won't go over it much. Now here is another interesting observation that we found out in the games played by our bot in the tournament. So now, as can be seen on the figure, we have plotted the move comparison against every other bot in the tournament. So here we can see that similar to a real chess player, Pianchetto wins the games quickly against lower rated bots, whereas the game extends to a larger duration against higher rated bots. Now, at last, I would like to mention some key areas where further improvements could still be made. Now, owing to the limited time and resource constraints, we were not able to tune the parameters to an optimal combination. Hence, tuning the parameters related to score functions could be a further improvement and could provide further improvement in Fianchetto's performance. Now, the board set size in endgames increases exponentially as the probability of sensing the opponent's moves correctly reduces. So maintaining a lower board set size or developing a planning strategy for endgame specifically could still be a key area of improvement for our bot. As it stands, the two strategies of sensing and moving of Strangefish 1 and our bot are still independent from each other. So coming up with a strategy that exploits the correlation between the two could be a possibility of improvement. Now, finally, instead of using a standard chess engine with some added heuristics as a proxy, the performance of the bot can, I think, significantly be improved by learning a dedicated evaluation function for RBC itself. I would also like to mention that we will soon be making a public release of our code, so it would help in further research in the particular game of RBC, and so that will help in building the bots next year. So thank you. If you have any questions that you would like to ask, we'll be more than happy to answer them.
Wow, thank you. I'll start. I certainly have questions. I thought that was a great presentation. And I'm really excited to see you carved open my 2019 code and made some really big improvements. I'll focus on the improvement that really surprised me, which was your propagation of board state probability over turns. And I have sort of always thought, well, I wish I could do that. But in my own experience, my estimate of what the opponent would do wasn't accurate enough. And so what I risked was weighting a board way too high or way too low. At the current moment, just because of the path it took to get there. Say I'm facing an opponent that recognizes that a path through some traditionally bad states ends up being very good. So I conservatively say, well, if the state's good now, then we'll give the opponent credit for doing that. And I see that your estimates now using LC0 come from a totally different source. So maybe you didn't experience that, but that's my question is, do you have any data or just kind of anecdotal experience on opponents that are more or less accurately predicted by this code? Did you have problems keeping track of their probabilities, or generally were you able to reflect what they truly did in the game?
Yeah, so I think that certainly is one issue with this particular like maintaining this board belief like this. Like for example, I think against some games of Penumbra, Penumbra plays certain moves that are like very like not good moves in chess, but they like plan for a mate in 2 or 3 in RBC. So since we like take the probabilities from LC0, those moves are not given a higher probability, and then the board beliefs for those particular boards are given a low weightage. And so like certain attacks were definitely possible against our bots. But I think what worked out in the end in general was that I think most of the agents were utilizing some engine or the other, whether it was Stockfish or LC0 or something else. And since they were using these engines, the probability from LC0 along with the uniform distribution unbiasing helped us in like estimating what could be the board belief. So one particular, I think, statistic is that we were able to like if we arrange the boards according to their belief probability, the true board state was always, I think, within the top 50 to 100 boards. So yeah, so it's certainly an issue, but as of now, I think since most of the bots use a variant of chess engine, this particular change actually helped us a lot.
I have some questions as well, but I know Kevin, I think I saw your hand up, and I think I saw Greg's hand up, and then there may have been others that I didn't see. Were your questions answered?
My hand wasn't up, but I do have. Oh yeah, I was also clapping.
Oh,
They were
clapping. Oh,
clapping.
I'm sorry.
Yes,
I'm notoriously bad at understanding modern technology.
But yeah, I can go. I mean, so actually, just based on that. Well, actually, first I should say that this is a really nice presentation and really good job to you guys. But yeah, going off of actually what Gino asked, so I know you guys said you added a uniform distribution to this part as well. So 2 questions. One, was that also part of V2? And 2, did you, yeah, how did you find that adding the uniform distribution affected the performance of the bot? Like, did you have to tune that to find the right balance? Yeah, how was that?
Yeah, so answering the first question, and that wasn't part of V2. So V2 was just estimating the opponent's move probability using the LC0 engine. It was actually part of V4, I think. Over here we discussed. So actually, like adding this so that weight for the uniform probability actually changes throughout the game. So for example, initially we give a higher weightage to LC0 engine's probability, and then we keep increasing the weightage on uniform distribution as the game progresses. So that's like majorly because of 2 reasons. First one being that it was helping us in like maintaining a lesser board size, because as the game was progressing, the number of moves that the different agents were playing according to the engine was decreasing. So it was helping us to unbias that particular bias that was coming from the LC0 engine. And so that eventually like helped us in also decreasing the board set size, since the sensing strategy itself was getting improved using this. So yeah, so this particular change, I think, helped us in that sense. And so like a increase from V3 to V4 was like can be seen because of both of these changes of like adding the uniform distribution and this like adjusting the weights for both set reduction throughout the game.
Cool, interesting.
Yeah.
So for just V2, you just use the alpha zero, or sorry, the L0 probabilities. And
Yeah.
what do those
You-
usually look
along with
like?
this update.
Like, are they usually like 100% and 0%, or like do they usually have like long tails?
Yeah. So I think that like no particular move actually reaches 100%. Even like, for example, we were analyzing some end games or like some mate and twos and threes, and even in those cases, like the probabilities were not going to 100%. In the sense that, let's say, if there's a particular mate in one with only one single move, then that was getting like, I think, around a 60% probability, whereas some other move was getting 10, 20. And I think that
I
was
see.
because like, even though there's a mate in one, if we play some other move, there's still a mate in one. So I think LC0 doesn't give like all
Yeah.
of its probability to a single move in most cases.
Cool, thanks.
Yeah, this is fantastic. Thanks for the very clear presentation, Mohammed. And I'm also excited that you're open sourcing your code. That's great. So I have some questions as well, but we are starting to accumulate some amount of delay in schedule here. So I may ask you offline. But if anyone else has questions they would like to ask, you can speak now or forever hold your peace. Otherwise, we'll move on. Okay, well, thank you again. Congratulations to you and your team. That was great. So next we have. Next we have Lucas McCabe with Urchin, maybe, or he can fix my pronunciation.
Hi. Honestly, that was so good that I'd be totally happy to forego my 10 minutes for more discussion. The previous one. So hi, my name is Lucas. I'm a data scientist at the Logistics Management Institute. My background's mostly discrete math, so this has been a fun foray into something new for me. Urchin came in with three goals rather. First was build something with a fairly low computational load. The second one was do it really quickly, because we started work on this after pretty much everybody already had working prototypes, and both of the practice competitions had already passed. So our actual tournament entry was still trying to figure out how to manage simultaneous play and stuff like that. So we were still figuring things out. Since then, we've run some experiments and that we think we could be a little bit interesting to share. And then our third goal was to see how well a language model could help with some of these problems. Just to confirm, can everybody see my slides? Okay, cool. Thanks.
Yeah.
So at a glance, the best approach that we consider here in our experiments consists of a very crude probability distribution over the state space, very optimistic move selection, and then a sense strategy that usually minimizes the number of possible moves, but sometimes senses to search for good attacks. In our experiments, this version doesn't do as well as the top few teams. So I don't claim to have like state-of-the-art performance or anything like that, but it is comparable to maybe the 7th or 8th place in the tournament when we look at win rate versus baselines. So in our game tree, every node is an individual move. I think other people probably do something similar. We do our best to keep track of every possible game state, just like Strangefish, and obviously we delete nodes when they conflict with the information that we get from the game. So either by sensing or by failing a move or by having a capture or something like that. And like others have done before, we found that when this possible state space gets too large for us to evaluate quickly, we just uniformly downsample and continue from there. Somebody 2 years ago, I saw one of the videos recently, pointed out that uniformly downsampling actually does pretty well, because in general, chess is kind of clumpy and that there's a lot of ways to get to the same place. But for us, we found that it was really inefficient to analyze every possible game state. So for example, here's a few representative game states from move 24 of a game that we played the other day. We had 214 possible states that we were tracking at this point. So what we see is that they present vastly different risks to white, right? In the top left, there's an easy rook capture. Immediately to the right of that, there's white's in check. And then everything else seems pretty benign. Just as an aside, we also keep track of the backup board, which is just this like pseudo legal board. It's the same state that Troutbot tracks. We use that later. So it'd be nice to have some kind of probability distribution over possible states. And we thought it would be interesting to see if we could use the language model to do this. So that's the unsupervised representations part of Urchin. So we just convert every move to its short algebraic notation. And the reason we do that is we're more interested in what specific piece is doing what or going where, rather than just like, oh, I have some piece that moved from here to there. And then we just throw this at word2vec. We started our training with 3.5 million chess games from ChessDB, and then we update the model after every Reconnaissance blind chess game. So when it's our turn to move, we uniformly sample 250 possible states, or whatever the max is if there's fewer than that. And then we have the language model throw out the bottom 90% lowest probability states, and the remaining 10% are what we analyze to move. In the tournament, we also use this to model to prune low probability states from the tree. But this ended up being a terrible idea because you end up being way too aggressive and throwing out totally legitimate possibilities, especially against quote unquote unlikely opponents. So for example, like attacker bot. There's some obvious issues with this strategy. The main one being that our initial training is based on perfect information games where players were really good. The average ELO was over 2,200 in that database. So like move sequences in RBC look super different than players' moves would look in conventional chess. So for example, you have to be really careful not to get hit by a quick attack like bishop to b5 early in the game, which would probably not be super successful in a high-level conventional tournament. That being said, we found this sampling strategy was great because our move processing engine wasn't very fast, and so we didn't have to consider so many states. Our primary sense strategy is just to reduce the size of the game tree as much as possible and to be quick about it using some matrix stuff. We use this matrix that just represents the number of unique pieces at each square across all the possible states we track. And we just pick the 3x3 box that has the largest sum in the matrix. This isn't an exact method of reducing the state space, but it actually worked pretty well for our purposes. We maybe only had to downsample on average maybe once or twice per game in our most recent experiments. Something we did not find useful was deleting leaf nodes that produced duplicate game states. This is super computationally expensive on our end because we're representing every node by its move token. So you ended up having to check for permutations of those sequences. And honestly, you probably want the repeats in there anyway, so that the uniform downsampling preserves the clumpiness attractive behavior. So under fixed time constraints, I think it's just better to analyze more states less thoroughly than to look at fewer states, but search deeper into the game tree. I think the intuition for this is probably that planning for the very long term is pretty risky if there's a lot of uncertainty. So it might be better to just look shorter in the term and add a lot of possibilities. So I'll just talk about 3 strategies, minimax, best average, and maximax. Our primary metric of interest is not the centipon advantage because we wanted to be more careful about comparing possible states. So the metric of interest that we're using is the expected difference in win probability or expected win probability made by a move on a particular board. And I'll just call this score for brevity. So, so our pessimistic algorithm is for each legal move, what's the lowest score it gets across all the boards that we're considering. And we select the best move in the worst case. I really thought that that was going to be the best one. I thought that being conservative with all the uncertainty was a good idea. But I think now, in retrospect, it seems like a terrible idea because you end up with much longer games and not a lot of interesting attacks and stuff like that. For these decision rules, I'm just reporting the win rate versus from 20 games against Troutbot, which is a Stockfish baseline that APL provided. It's actually a pretty decent baseline, just all things considered. It came in 12th in the competition. Best average selects the move with the highest average score across the boards we're considering. So from conversations with some other people, I thought that this would do a lot better, but in our experiments for our framework, it was neck and neck with Troutbot. But a very optimistic strategy that selects the best move in the best case did the best of all 3. And we can actually do a little bit better than this by very crudely integrating sense strategy with move strategy. So what we tried was looking at that backup board, which is the board that Troutbot tracks as its state. If we think that we can take a king or a queen, sense there just to check. If not, look around and see if there's any high value pieces and there's like a ranking to that. And if we think that we can take one of those, then do so with 30% probability. The 30% is kind of arbitrary in the most specific sense, but the idea was to have something that was substantially less than 50%, because if it's more than 30% or so, we start to get runaway tracking of the state space, and so it gets too large. But below, say 20% or so, we're just not doing it frequently enough for it to be useful. And then otherwise, just use your original sensing algorithm. This version had a 75% win rate versus Troutbot, which is not as good as some of the top few teams, but is roughly on par with, say, the 7th or 8th place in the tournament. So just some final thoughts that I thought were kind of interesting as observations. Going for lots of attacks alone isn't super desirable, since you're revealing a lot of information about where you are. So I liked the comment about how pawn attacks are really useful. That was an interesting kind of nuance to the statement as well. But the other thing is that the best decision rule is probably going to depend on your sampling strategy, if you're sampling. Our position is that only analyzing your highest probability states allows you to use a slightly more aggressive decision rule when moving. But ideally, I think that the right decision rule, if you're using a decision rule, probably varies throughout the game. Moving forward, I think it makes sense to kind of refine the distribution over state space idea and employ that for an expectimax decision rule when moving. But otherwise, it seems like all aspects of the game work better when they're more synchronous. So this makes me think that a multitask approach might be a sensible direction as well. I guess before I finish, I just want to thank good folks of Johns Hopkins Applied Physics Lab for developing such an interesting test bed for sequential decision-making under uncertainty, and also running just a seamless competition and working so hard to foster a development community around this game. I really appreciate that. Thanks. I'm done.
Thanks.
Yeah,
Thank you for the great presentation. We have any questions on on Urchin. I have, oh,
I didn't have
great.
any. Well, I just wanted to say, great job with your presentation. You just did such a good job. I guess I was sort of wondering about, so your Maximax algorithm, why that in particular? So being optimistic about the moves that your opponent made ended up leading to your bot having better performance. I was wondering if you could tell a little bit more about that.
Yeah, I want to be clear about what I mean by optimistic. I'm not making any statements about what my opponent did. So what I'm saying is I'm taking the board where I'm taking the move where across all the possible states, that move did the best, if that makes sense. Right, so I'm taking every legal move and I'm testing it on every board that I want to consider. And I'm taking the max score across all those boards. And then once I have those for each move, I'm taking the max move among those. So I just want to clarify that's what I meant by optimistic.
Great, thank you so much, and good job.
Thanks.
I see. So in all of those, Lucas, like your mini max, you're considering the first min or max is referring to it's across all moves, and the second one is across all boards, or vice versa.
Vice versa.
Yeah. Okay.
So the mini max was what I'm saving across all the boards is the worst case scenario for that move, right? And then I'm taking the best of those for the mini max.
And yeah, another unrelated question. When for your language model, is that something you ended up using or trying?
It's something that I ended up using.
Okay.
It actually works fairly well for my purposes because I wasn't able to efficiently use these decision rules on all the states that I was considering at the time. I think that some competitors were better about sensing than I was, and so and still am. I want to make it clear that these are from experiments I've done since the tournament, not the results of the tournament itself, if that makes sense.
Yeah, gotcha.
Yeah, but yes, it is something that I continue to use. I think that there's some interesting modifications that I could do to make it work a little bit better, but ended up serving its purpose for me.
Yeah, that's pretty cool. We haven't seen anyone use a language model before. I know you said that there were problems with you trained on these really good chess games. Did you end up training on RBC data as well, were you saying, or?
Yeah.
Okay.
Yeah, it's just that in order to get the language model up and running initially, I trained on this giant database of really good players in perfect information games. After every RBC game, I update the model with that game, but it's really overwhelmed by the fact that in the beginning, 3.5 million training examples were of a fundamentally different game.
Okay. Were you training on your own games? Were you saying? I mean, anyway, okay. So we do have the histories also on there. If you want to, anyway, for everyone's information, if you want to use them, we do have pretty good set of games at this point.
Yeah, I think that's a great idea, and something that's one of the things that I'd like to do is just take all those records that you guys have and use that instead. But that's not what I did.
Yep. Understood. Yeah. I think we all have a long list of things we would like to do.
Definitely.
Yep.
Among those, just because this has come up a couple of times in communications leading up to this, on the to-do list is to provide a better tool for bulk downloading. The server now has recently crossed 400,000 games, and the only tool available for getting those for you all is individual querying. which you're allowed to do, but is not very practical. So keep an eye out. I will update that with a tool for getting larger batches all at once and let you know when that's done. For the sake of time, we should go on to the next presentation. We're going to hear, if I've got the schedule right, next from Gregory Clark, who authored Penumbra.
And
Sounds good to me.
I'll add Gregory Clark was the winner of our. We didn't apply to do a NeurIPS competition with the COVID and everything for 2020, but we had a just an online challenge, and Gregory was the winner of that, and he also spoke at our 2019 NeurIPS.
Am I presenting?
You
Yes.
are.
Cool. Okay, I'll get started. So my bot was Penumbra, and it was created, as Ryan just said, for the 2019 NeurIPS competition. It's written in Go mostly, and it uses a TensorFlow network. And in 2019, it performed worse than the random bot, which was a little bit frustrating. In 2020, it came back and won the official rating competition. It might have gotten a little bit lucky there, but I'll take it. And this year it placed second or third or fourth, depending on how you count. Kevin definitely played better, but missed more games. I also had 2 separate internet outages during the tournament, but they didn't make a difference. All 3 of these versions essentially use the same algorithm though. So I'll first talk about the differences between the versions and then the algorithm. From 2019 to 2020, I connected all 4 of the GPUs to the power supply. That was an important step. And fixed a critical bug in the playout code by adding a single break statement. And it made a huge difference because then I chose according to the prior probabilities instead of always choosing the last move. So here's a reminder, always unit test your code, even if it's stochastic and you think, oh, I can't test that. Find a way, it's worth it. And the network was retrained on much more example historical data, which made a big difference. And I introduced some ideas of like caution and paranoia, which turned out not to be very important. And then the changes from last year to this year are that I retrained the network and tweaked some hyperparameters and not much else. How does it play though? So imperfect information games against fixed opponents are partially observable Markov decision processes. We can just consider the opponent part of the environment. And so there's an algorithm called partially observable Monte Carlo planning from David Silver and Joel Van Ness for POMDPs that tracks state with a particle filter and plans with upper confidence bound tree search over observation histories as nodes. And Penumbra uses a variation of that algorithm that I dubbed deep synoptic Monte Carlo planning. DSMCP, this algorithm, truncates information sets to a limited manageable size. So at the root, it tracks all possible positions, but then in the tree search and in the particle filter, it limits the number of possible placements to 128. And those are uniformly randomly chosen when there are more than 128. And then it uses those approximate information states to build belief states about the position. So it accumulates a set of possible states from the opponent's perspective. And this second order representation allows the algorithm to account for opponent's uncertainty to some extent at least. And the algorithm tracks belief states for each turn using a particle filter. So here we're sampling from the previous turn and then updating according to prior probabilities provided by a neural network. And it plans with upper confidence bound tree search, where each node is like a multi-armed bandit, where you try some a certain number of times according to the bandit algorithm, and each node is also a pair of approximate information states. So trying to cram all of that into one picture, the algorithm uses a particle filter to track state, and it also tracks all of the possible placements at the root node and samples from the opponent's, like our belief about what the opponent thinks, and samples from possible placements, and uses that to build a tree, build a search tree. And all of the whole search is guided by a neural network that is trained on historical data. It has, this is a figure from a paper that I wrote about last year's version, and you're welcome to read that paper for more details. For this competition, I think I actually added like 2 more residual blocks, something like that. But it was basically the same network. And it has a bunch of headsets, one for each opponent, that like model specific opponents. And it's not obvious how to send these circles, these sets of placements, these sets of positions to a neural network. How do you represent that? How do you abstract the possible states? And Penumbra uses a stochastic abstraction. So we're sampling down to a limited size. That's the stochastic part. And then, okay, I'll just read through the slide. Many games admit a compact representation of each information state. For example, poker. In poker, a history of observations suffices to fully represent an information state. However, observation histories in RBC are not bounded in size, and it's not obvious how to use them as input to a neural network. So DSMCP uses synopses of approximate information states. And so the synopsis function takes a set of positions and, oh, can you not see me? I just realized my camera is not on.
We can see
Yeah, we
your
can see
slide
you.
though.
Okay, I'll just keep going. The synopsis function maps a set of possible placements to a fixed size set of binary features that can then be used as input to the neural network. And I use a somewhat like a novel stochastic bandit algorithm to mix in the network policy. It's basically the same thing as what is used in AlphaGo, but a small percentage of the time, or a high percentage of the time when we're first visiting a node, we choose randomly according to the network's policy instead of according to the bandit algorithm. And this actually helped quite a bit in some experiments. This algorithm models each opponent based on historical data and seeks a best response strategy to exploit predictable behavior. However, the algorithm itself may be exploitable since it does not seek a Nash equilibrium strategy. Here's some experimental results from the paper that's at NeurIPS this year. Penumbra was stronger than baselines. You all have created stronger programs though. And oh, and all of the data, all of the games played to create this table are available for download. I have a link on my GitHub or something like that. So it's like 80,000 more games if the ones that are on the Johns Hopkins website are not enough. And here's a graph that shows that the network does penalize uncertainty. And here's an evaluation of the various parts of the specific synopsis function used by Penumbra, which basically says that the stage and the last opposing capture, like the location of the last capture, are by far the two most useful signals. And that's my presentation. There's a paper on arXiv, and it will be presented in approximately 1.5 days at NeurIPS. So please feel free to stop by the poster session.
Yeah, congrats on getting the paper in, Greg. That's great.
Thank you.
Does anyone have any questions for Greg? I will say one of my favorite things, I really like that this bot models the opponents, because I mean, to me, that's one of the interesting problems here is, I don't know, I guess I'm imagining that the person who always plays rock, I know like most of the bots would actually not, play paper all the time in that case, to create the analogy.
Yeah, if you play a bunch of games where you always play one thing though, this algorithm will get confused if it trains on your historical information.
Right, yep, like you were mentioning. It's a good point.
I think there's a future step is to use offline RL. I think that has potential to create a stronger bot instead of like just treating the training process as a supervised learning task.
You were saying using offline?
Yeah,
VR, you said
offline
RL,
RL or batch RL is the older name for that field. Yeah.
Well, that sort of leads into my question, which is what's next for this bot? You have an idea of what you want to do?
I would love to spend more time on this. I think offline RL is the most straightforward. That feels most promising to me. And the other thing that needs to be fixed is that right now, this bot doesn't seek a Nash equilibrium. I forget where that slide is. I probably passed it. To use an algorithm that actually finds a Nash equilibrium strategy.
I have a question.
Mm-hmm.
So where do the synopsis, those binary functions come from?
They're handcrafted in this example, and they're all fairly, I think they're kind of straightforward. So the first 10 here are all constant. They're just describing some information about chessboards, which makes sense to do because the network is a convolutional neural network that otherwise won't necessarily, like that information is valuable to the network. And then after that, there are the locations of your own pieces. So you definitely know where they are, and that's important to let the network know where they are also. And then after that, it's like all of the locations where there might be an opposing knight. Like number 27 is all of the places where there might be an opposing knight. And so this is just a specific instance. And there are like squares where a piece could attack the king from, and things like that. It's just a bunch of bitwise programming. I have descriptions, like text descriptions of all of them in the paper.
Would it be possible
Some of them are near.
Sorry, go ahead.
Some of them are near duplicates of each other and could probably be dropped. Your turn.
Would it be possible to learn, instead of handcrafting these, to learn these?
Yeah, so there's the bitter lesson, which essentially says using data to make decisions generally leads to better outcomes than trying to handcraft things. And so, yeah, probably. It's not clear to me how to do that, but that is another good idea for future work.
I see. Yeah, I don't know if you've seen, but this, especially the graph that you have a couple slides after this, is really reminiscent of the new DeepMind paper that shows what human concepts AlphaZero learned. I don't know if you've seen that, but it also has kind of graphs that show how important various features are, but those features were learned. Well, the features that they picked, most of them are, I don't actually read the paper, but it's I think they're like handcrafted features, and they see if AlphaZero learned something corresponding to those or something like that.
Could you drop the link to that paper in the chat?
Yeah.
I'm interested.
Are there any other questions for Greg? Thanks a lot, Greg. And so next we have Brady Garrison with Garrison NRL.
Thank you very much. Hello, everybody. My name is Brady Garrison. I'm a senior at Pembroke Pines Charter High School in Pembroke Pines, Florida. I live in Miramar, Florida. And I am a virtual intern with the Naval Research Laboratory in Washington, D.C. Through the Science and Engineering Apprenticeship Program. My project mentor is Dr. Prithviraj Dasgupta, and he works with the Distributed Intelligence Systems section. And this is my presentation on Garrison NRL, the bot that I used to compete in this tournament. So to begin with, what is Garrison NRL? Garrison NRL is based on the multi-hypothesis tracking bot from Markowitz et al. In 2019. It keeps track of a set of potential board states to use for sensing a movement, and then uses abstractions and existing chess programming tools to manage these board states, make the best decisions possible. So as you can see on the right, Garrison NRL typically had an ELO ranging from 1100 to 1200 throughout its time on Johns Hopkins University servers, and finished a total of 2,500 games. So what is the multi-hypothesis tracking bot? The multi-hypothesis tracking bot, or MHT bot, keeps track of all the potential board states. It doesn't make any assumptions about its opponent. In order to expand the size of its board states, it makes every potential opponent move from the current set of boards, and this makes it adaptable to a wide range of strategies. In order to choose a sensing action, it looks at every board in the potential boards, and then chooses a square where the most potential opponent moves could be. So this sense choice minimizes the potential board states by eliminating boards based upon the result. To choose movement action, MHTBot chooses the best Stockfish move for every board in the current board set, and then selects the mode of those best moves. So I adapted the strategies used in multi-hypothesis tracking bot for Garrison NRL. So for every board in its current, for Garrison NRL's sensing strategy, it looks at every board in its current board set, and then first counts the number of potential opponent moves to a location. So this is very similar to the way that multi-hypothesis tracking bot does its sensing action. But then the way that Garrison NRL differs is that it next totals the piece scores for potential opponent moves to a location. It uses the traditional chess scoring system shown to the top right, counting the king as equivalent to the queen. And then third, it multiplies these two values, the number of potential opponent moves to location and the aggregate scores at a location, to create a sensing weight where the score of the maximum sensing weight is chosen for the sensing action. So in this way, Garrison NRL chooses the square with the most potential boards and the highest aggregate scores, getting a sense that minimizes the number of boards. So to make movement decisions, the bot selects the best move for each board in its board set based upon the following methods in order of priority. So first, if there are pieces attacking the opponent king, we'll select one of these attacks as the best move to attempt to capture the opponent king and win the game. Second, we'll use the Leela Chess Zero engine loaded with the Maya 1700 train network and CZG 345 endgame table bases to select the best move. And then third, if the chess engine crashes, we'll reboot and attempt a random move. So from this set of best moves, the mode and second mode as a backup are selected, and if both the mode and the backup are illegal moves or blank, a random move is played instead. So now I want to discuss some abstractions that I used for Garrison NRL. So for maintaining Garrison NRL's board set, I used uniform random sampling to limit the size of the board set. So as the game proceeds, Garrison NRL expands its board states by adding a new board for each potential opponent move for every current potential board. However, this approach results in an exponentially increasing board set due to the large number of potential boards and moves. And this board set very quickly becomes impossible to manage for my laptop, which is a HPMV with a normal standard CPU and no GPU. And this very quickly stopped my bot from functioning. So instead, I decided to randomly eliminate board states by doing random samples of 200 boards throughout the game. So by taking representative samples, I was able to get boards that were able to represent current state of the game while still keeping the board set at a low enough number so that my computer would be able to function. So in this way, I was able to balance functionality in terms of playing the game with functionality in terms of computation power. So then the other important abstraction that I did was limiting sensing actions. So to avoid senses on the edges and corners of the board that unnecessarily misinformation, I instead eliminate senses on the corners and edges of the board and move instead to the next closest center square. So in this way, Garrison NRL gains the maximum amount of information from each of its senses, gaining 9 squares of information from every sense that it makes, rather than going on the edges of the corners and losing potential information that it wouldn't get otherwise. So this was a good way to improve the performance of my bot relatively quickly. It's a very helpful method to use. So now I want to discuss some of the chess programming tools that I used for Garrison NRL. So one of the first and most important ones that I used was Leela Chess Zero. So instead of using Stockfish for my bot, I decided to use the Leela Chess Zero engine, which loads trained neural networks in order to make decisions and then uses the universal chess interface, making it very good to work with reconnaissance blind chess. So I used the Maya 1700 trained network, which learned to play chess from millions of online games between humans rather than self-play, and is intended to get human-like moves. So this engine setup came with the following advantages. So first, I could test a variety of neural networks through Leela chess to find the network that's most suited for reconnaissance blind chess. Second, Leela chess has a variety of variations with different CPU and GPU specifications, so that I was able to select the one that was best for my hardware, similar to how Fianchetto used Leela chess in order to reduce the amount of time for their system. So this was helpful for making it work with my system. And then third, rather than playing the moves that are traditionally deemed best by Stockfish, human-like moves are played instead, which makes the moves from Garrison NRL less predictable by other bots, which tend to use more traditional chess moves and Stockfish chess engine. So then the other most important tool that I used for my bot were CZG endgame table bases. So endgame table bases are large information sets of chessboards with low number of pieces or endgames that have been compiled through retrograde analysis and give information as to how to make perfect play at the end of a chess game. So CZG provides a predicted outcome or a win-draw loss that includes metrics for forced draws and a depth to zero metric for all endgame positions of up to 7 pieces. For Garrison NRL, I decided to use the 3, 4, 5 piece CZG tables. To evaluate these endgame table bases and achieve perfect play, a minimax algorithm with alpha beta pruning may be used. So Garrison NRL uses these table bases to make decisions about movements and make better cutoffs to its board set rather than uniform random sampling. It uses the CZG endgame win-draw loss ratios to prune the number of boards in its board set. And this happens when the game falls into an endgame state or a very low number of pieces. So in addition, CZG tables can be loaded onto chess engines like Leela Chess and Stockfish, which improve their performance later in the game and give them more information upon which to make decisions. So another chess programming tool that I considered using were polyglot opening books, but I ended up deciding not to use this tool for the tournament build. So these opening books compile opening movements from thousands of Grandmaster games to create a weighted distribution of good openings. And then these books come in a variety of, from compilations of varieties of games that are formatted into .bin files. So I tried adding another layer to the Garrison NRL movement strategy to make movements based upon a polyglot opening book before a chess engine. However, this only kept performance the same or worse, as most chess engines already include effective opening strategies from their heuristics, and then also the many potential boards of reconnaissance blind chess prevent meaningful opening strategies from being made with opening books. So I decided not to use this tool during the tournament build of Garrison NRL. However, in the future, I hope that I'll be able to come up with a good way to improve opening strategies for reconnaissance blind chess. So to summarize, Garrison NRL is based on the multi-hypothesis tracking bot, maintains a library of board states that is limited through uniform random sampling. The Garrison NRL sensing strategy utilizes p-scores in the board set to determine the sense of the highest value, and then limits the sense to the middle of the board. The Garrison NRL movement strategy uses Leela Chess 0 loaded with the Maya 1700 network. It also loads CZG 345 table bases to better inform movements. So I also wanted to summarize the results of Garrison NRL at this tournament and what I plan to do in the future. So Garrison NRL ended up placing 11th at the NeurIPS tournament with an ELO of 1140. So my bot was able to outperform baselines like Trout, Tacker, and Random. It was also able to beat every other bot at least once, which are results that I'm very happy with and were goals that I had for this coming into this tournament. In the future, I plan to continue integrating new algorithms like Monte Carlo tree search and reinforcement learning with Markov decision processes. I hope to be able to make competent strategies for opening and late game decisions to potentially simplify the game reconnaissance blind chess in terms of openings, endgames, and middle game. I plan to continue participating in Reconnaissance blind chess tournaments in the future with these approaches. I also wanted to acknowledge everybody who made it possible for me to be here today. I wanted to thank in particular my mentor, Dr. Raj Dasgupta, for providing me with the guidance throughout this process and helping me to think about how to program for Reconnaissance blind chess. I wanted to thank the Office of Naval Research for giving me the opportunity to apply for the Science and Engineering Apprenticeship Program. And I wanted to thank the Distributed Intelligence System section of NRL for accepting me to be one of their interns. I also wanted to thank the Johns Hopkins Applied Physics Laboratory Intelligent System Center for making this competition and making it open source so that I'd be able to compete and making the tournament available for anyone to register. Here's the related works to everything in my presentation and sources for images. And I'm really honored to compete among all of you and have the opportunity to participate in this competition. Thank you so much for listening to my presentation. And if anybody has any questions, they could ask me now or towards the end of the conference.
Thanks, Brady. Yeah, congratulations on being a high schooler, making a respectable bot. That's awesome.
Thank you so much. I really appreciate it.
Does anyone have any questions for Brady?
How confident are you that the table bases are correct for Reconnaissance blind chess? I could imagine that there might be some positions with very few pieces where you might want to play something different given the uncertainty.
Well, that actually, I'm actually pretty sure that you may be right about that. Well, the one thing in particular with the endgame table bases is that, well, in Reconnaissance blind chess, there isn't really the concept of check or checkmate. So these endgame table bases were generated with that in mind. So that may actually affect whether or not they have perfect play towards the end. But hopefully, but Garrison NRL usually makes decisions based upon attacking the opponent king first to attempt to win the game. But the endgame table bases are actually generated to have perfect play towards the end of the chess game. And they're still continuing work to expand the number of pieces that perfect play could be generated for. But that definitely is something worth considering, that if these kinds of table bases can be generated with the rules of Reconnaissance blind chess in mind, that might be a better way to make decisions in the end game, which is something that I'd like to work on in the future. And then right with imperfect information, of course, you don't necessarily know what end game you're in with those table bases. But yeah, that's definitely worth thinking about.
So even if we remove out the uncertainty part of RBC, right, there is still a added pass move that is added to the game, right, which is not there in the standard chess, right? So when you look at a particular end game, right, in standard chess, there is a fixed strategy of winning that particular game if it's possible, right? And the same strategy won't work for RBC because the opponent now has a pass move, right? So that also isn't incorporated in any of the tables, right? So I can simply create a situation in which there are two moves, both of them are perfectly winning for the standard chess, but one of them is basically actually a draw for RBC. So that is one thing that definitely I think something needs to be done so that we can use that better, right?
Yeah, I definitely agree with that for sure. The pass move does sort of introduce a new layer of strategy as well.
Yeah.
It's important to consider. Which also is why it was hard to use the opening books because, well, mainly just because there are so many different boards that using that tool, well, it sort of becomes irrelevant because for 10 different boards, you may select 10 different approaches to the opening. And then even in some of them, people may pass, which isn't normally considered in those opening books. But I would like to generate new tools that could do that.
Thanks for the discussion on that. I think for time, we've got 3 presentations left. So we'll move on to hear from the author of NASH, Eaton Rothberg. Sorry if I pronounced that wrong.
No, you got it. Yeah, Eitan.
Great.
Yeah, I can share my screen here. So okay, yeah. Hey, so I'm Eitan. I'm running on San Francisco time, so it's getting up to 4 or 5 in the morning. So if I stop making sense at any point, just give a holler and slow me down.
Understood. Itan, I don't think I can't see your slides unless.
Yeah, I'm having trouble sharing them.
Okay.
Oh, okay.
Excuse me, that may have been my bad.
No worries. Can you see this now? Okay. Awesome.
Yes.
Cool. So so I got to work on Nash with my brother Carmi. Had a great time doing it. So I'm excited to share a little bit about what I learned and how it works. So I'll talk just a little bit, I guess, about how we sort of thought about states for the game, as well as just how we chose senses, how we chose movements, and a little bit about clock management. So to start, so when we talked about state, we decided to treat it as basically all of the possible boards like all of the possible boards, as well as every board that our opponent could believe to be possible. So we were keeping track of the probability of every board and our understanding of the opponent's probabilities of every board. So we sort of decided to cut it off at that second degree of knowledge. So we were sort of torn about maybe even going one step further and considering like what we think they think we think. We decided to cut it off there. And then in order to sort of facilitate this, we treated it as the opponent using the same sensing and movement strategy that we were using, so to try to keep this as sort of some concept of common knowledge, or at least a modified version, to let us work towards a Nash equilibrium, or at least a Nash equilibrium, a modified Nash equilibrium kind of idea, where we're choosing moves and assuming they know how we're choosing moves. So for selecting sense actions, we just chose like a really straightforward strategy to minimize uncertainty. So we took the sum of all the different board probabilities and we tried to minimize that. So best case scenario, we only have one board. Worse than that would be to have two boards with extreme probabilities like 0.9 and 0.1. Worse than that would be to have two boards with equal probabilities, and then so on and so forth from there. So we just tried just a really basic strategy for minimizing uncertainty for sensing. For selecting moves, we did something more interesting. So the basic idea was to evaluate moves on a bunch of boards and then weight the evaluations by the board probabilities. So if a move turned out to be really strong on a board that was highly likely, then we gave that move a very strong score, and then we selected moves proportionately to those valuations. And so the idea with this is that it was sort of supposed to be some like baseline approximation of Nash equilibrium that we could later iterate on. But that's sort of the intuition there. Because we weren't using, or I hadn't thought to try out the Leela Chess Zero like batch sampling, I was running consistently into a case where I wasn't able to evaluate all of the moves on all of the boards. So I implemented a sampling algorithm where we basically start off by finding like how promising each move is, or so like how well has it done so far, and how likely or how unexplored is that move on the main boards. So if it's shown to be very strong so far and we haven't tried it out on a board that's highly likely, then it's a strong candidate to be evaluated. And once we had sort of those like exploration scores for each move, then we looked at the boards that needed to be evaluated the most, and we evaluated the moves with the highest exploration scores on the boards with the highest exploration scores, and we did this iteratively until we ran out of time for a given turn. The way that we actually evaluated moves on specific boards was just using a chess engine. We just used Stockfish. So first we evaluated, we played the move on the board and evaluated the new board. And then if the move wasn't a capture, we would actually let the player who just made a move make another move. And the idea was sort of to like implicitly deal with situations like checks or like threatening like a queen without actually having to like explicitly use heuristics for it. So again, so it was just like a player would move and then we'd let them move again. And we'd sort of average out those two board scores. So like if a move like puts the opponent in check, but it's extremely risky, meaning if the opponent finds out that you do it, you'll lose a game, then it's not going to look good because you're averaging a very low score with a very high score. So less risky moves automatically get favored. So this is sort of what we're using as baseline. Eventually, I think this could be improved upon significantly, maybe with something iterative or something that at least like takes the context into account. We're storing all this information about what the opponent believes, or at least what we think the opponent believes. And so it would be beneficial to leverage that at some point, maybe as some in-between thing before we evaluate the second board. And then just to talk a little bit about some clock management tools that ended up really coming in helpful for us, especially because we were keeping track of every possible state that we believed and every possible state that the opponent believed. The first one was to use like a special constant time bot that could take over like if we were running out of time. So we used just like a modified variant of chatbot, but I could also imagine using like a more specialized bot depending on the situation. So maybe one that specializes in endgames or just like at stalling, maybe some modified attacker bot. But I think using like some constant time bots to like take over in certain situations would be helpful. And then the last thing we did that made a big difference was we were constantly updating boards in the background. So rather than like downsampling and like throwing out boards altogether, we only used the most likely boards that we had for actually making decisions, while constantly updating the other boards in the background. And the idea was, if it ever turned out to be the case that the top end boards like no longer became options, then we could take from this sort of like background stash that we had been accumulating and propagating in the background. So that's pretty much it. So I want to say a huge thank you to everyone who put this together. I had a ton of fun participating in it, and I'm looking forward to continuing to do so.
Thank you. Happy to hear it. The live leaderboard will continue to be open, and I hope that's a general feeling among the participants. You know, there's more research to be done and more games to be played. Thanks for presenting. Does anybody have questions? We've got time for one or two.
Could you briefly say again, Eitan, how do you say Eitan or Eton?
Eitan, yeah, you got it.
How were you accounting for the opponent's uncertainty? I mean, how do you keep up with like 10 moves into the game since you don't really know what they've sensed?
Yeah, so actually I added one more slide on this. Let's see. So basically the idea is we're keeping track of a distribution over the possible boards. So probability of each board being the true board. And then for each of those possible boards, we keep track of what they would think if that board is the possible board. So right at the beginning, for example, after if we're playing black, after they move, right, there are 21 possible boards that we see. And for each of those boards, there's one possible board, right? That if that is a true state of the game, and they would only have one board in their distribution. But
Gotcha.
after we move, right, they would have 21 boards in each of those distributions. And so then for sensing, we look at each of those board distributions, and we say, if that were indeed the true one, what would they have sensed? And then how would they have condensed that distribution?
Oh, okay. Oh, cool. Cool.
Yeah, thanks.
Great. Thank you. Okay, I think as Gina was saying, I know we're taking up a lot of time here, so let's move on to Kevin Wang with Kevin Bot. Thanks again.
Hey, how's it going? I also have the same excuse if this goes terribly. I'm also on California time. Let's see. Present. So how do this? Oh no, this is okay. Can you guys see that?
Yes.
Okay, cool. So I didn't realize when I was making my account that the name I entered was going to be the name of my bot. So I didn't pick something cool like being Keto. So my bot is just named Kevin, which is also my name. So I worked for 2 years in tech in San Francisco, and I'm currently trying to get back into academia. So I'm doing research and applying to PhD programs right now. So if any of you guys know any professors who are looking for PhD students, let me know. So let me talk about my bot. So instead of directly talking about my approach, I'll first give an overview, and then I'll explain what I wanted to do, why that didn't work, and how that ended up being kind of a Frankenstein-y approach. But yeah, that was the result. So I'll explain the parts that I use at a high level. So I use Python, ran it on my laptop, which went to sleep later, but that's okay. I think like everyone else, I explicitly maintained a set of possible game states and a distribution, probability distribution over those. And I think I'm the first one so far who used CFR. So that stands for counterfactual regret minimization. So this is basically a way of finding a Nash equilibrium. So what I did is I make a depth limited subgame and then run CFR on that. And I use some heuristics for sensing. So what I wanted to do initially was basically approximate a Nash equilibrium in the game. So I really want to, use these. So I've been researching a lot of depth limited subgame solving in imperfect information games to find Nashes. So I wanted to try to do this for this game, which is a really new field of research, and I don't think anyone's really done it well yet. So that was my goal, and I wanted to kind of make a general algorithm, and maybe also enter it to the hidden information games competition that ended up getting canceled. So this is what my initial approach was going to be, which was maintain a distribution of possible game states, and then create this subgame. So yeah, this kind of depth limited subgame solving, as I think in Gina's earlier slides, it's really common in Ryan's earlier slides it's really common in perfect information games, right? Like in chess. So you'll do kind of let me just look ahead 6 moves ahead in the game. And then after those 6 moves, I'll just evaluate the state of the game and pretend that's my full game. I'll solve that game and that'll tell me what to do for my move. Yeah, that was the plan. Make a subgame, make it depth limited, use Stockfish to determine the values of the leaf nodes, and solve the subgame using CFR. And so this is there's this paper that came out right when I was starting this, actually, Brian Zhang and Tomas Sandholm. That's basically this approach. So one of the big problems, as mentioned earlier, with doing this kind of subgame solving is that the subgame is the public information state, which is huge. And so in this paper, they kind of say, oh, well, we can, instead of making it the public information state, we'll just make it, our information state. So we'll just kind of ignore all the states that my opponent thinks the game could be in, and just restrict it to game states that I think the game can be in. And they show that that's while it's not guaranteed to find a Nash, there are nice things about it, and it does work well in practice. And they showed that they did pretty good playing a different kind of blind chess. What's it called? Dark chess or something. So basically, I kind of just wanted to do something similar to that. But it didn't end up working. And the reason was that the CFR was taking too long. So I was running CFR using OpenSpiel, and I would run it for like 10, 20 seconds, which is kind of the upper bound of how long you take for a turn, right? And it was kind of giving terrible results. Like it would assign, like even if it was like a maiden in 2 or something, or like a maiden 1, it would assign probability to like really disastrous moves. So even when I use Monte Carlo CFR, which is should be faster and like not really looking super far ahead. And so the size of the sub games weren't even that big. It was like 10 to the 6 or something. So it really should have been possible. I think it was taking a really long time, maybe because I was using Python. There were a couple of layers of Python. I was doing implementations in OpenSpiel. In Python, OpenSpiel itself, I was using the Python wrappers around what's a C++ library. So there's a lot of Python in there. And so maybe if everything was written in C++, it might have been 10 times faster. And maybe my implementations were just really slow. And OpenSpiel itself, I think their implementations aren't exactly designed for performance. So like every time you perform an action, it's kind of expensive. And so when you do CFR, you're performing a lot of actions to traverse the game tree. So it's could be sped up. So yeah, so this is what I would want to do. And I still will try. But instead, I just use CFR for my opponent's moves, where the precision isn't as important. So you can kind of see how it's kind of a little Frankenstein-y, how I don't think anyone would think of this approach first off. But first I tried the other approach, didn't really work. And I was like, well, okay, I'll just use CFR for my opponent's moves. So that'll give me a probability distribution for my opponent's moves, assuming that they kind of play Nash. And it's not exactly accurate. It's got assigning some weird probability to some other moves, but it doesn't really matter that much because I'm just gonna choose how to best respond to that. And a little bit of fuzziness doesn't really matter that much. So here's some technical details on how that CFR worked. I used Monte Carlo CFR, and I only looked basically one move ahead. So I said, oh, if my opponent will consider what they can do, and they'll consider what I can do for one move. So I didn't really look that far ahead. So I don't even consider like 2 move, combinations. And then my bot makes its move greedily. So it ended up working pretty well. Yeah, ended up working pretty well. Although I made this meme, the duality of bot, showing that it still loses to attacker sometimes. And actually in the end, the day before the competition, I ended up hard coding performance against attacker. So I won every match in the actual competition. So yeah, okay. So I also have some heuristics for sensing that might be pretty interesting. I don't know if Strangefish or if other people do this, but so the first heuristic I used was maximizing entropy of a sense. So anytime you sense, it partitions the set of boards into a partition of subsets. So you can calculate the entropy for that, kind of like in a decision tree or something. And so you can just do that calculation and find the one with highest entropy. So I did that first, and then I found out that wasn't working that well because splitting the board doesn't really tell you everything, right? Or getting the most information doesn't tell you everything because there could be two subsets that both have the same best move, for example, and so you really care more about the outcome of your move, which I think someone mentioned. Strange Fitch does something similar to this. So this is my heuristic number 2 that I ended up using, and I think got a pretty big performance upgrade with this. So this, I basically just calculate the difference between the action that I would take. So for each actual board in the subset, after a sense partitions the boards into subsets, there's some actual best move, right? And then, but the subset itself also has a move that my bot will take if it knows that it's in that subset. And so there's some regret, which is, I'll say, is the difference between the score that it could have achieved if it took the best move and the score that it'll achieve if it moves. And so that gives another metric for what the best sense is. So that's what I ended up using. So here are the results. We already covered this. I just added this slide to show what I should have done on the left. Run this terminal command to keep my laptop awake, and I could have avoided what happened on the right. So some advice. And cannot load YouTube player. That's too bad. So that's basically it. I just want to say that the game is really good, and it's a really great spectator sport. Actually, here I'll share this video because it's pretty good. So I ended up. Let me see. How do I get this video? Yes, here we go. So I ended up making a really nice UI that I just want to show off. I made this basically terminal UI from which I could watch how my bot was doing as it ran, and it showed me what the 10 most probable states it thought it was in were, and the score, or how well it thought it was doing in each of those. And so I actually just wasted hours just watching this intently, and it was so much more exciting than I thought it would be. Just like being like, oh my god, it made a blunder. Oh, it's doing like a crazy tactical combination. And the swings in this game are much more exciting than real chess, as the chess championships right now aren't that bad. But let's see, do I have anything else?
Here is the yellow coloring where a sense happened.
Yes. The yellow coloring is the sense. Let's see. Yeah, let me just go back and share my last couple slides.
That is great. And you got some incredible performance out of your self-proclaimed Frankenstein of a bot. I think I think that fell into place pretty well. Better than you're selling it. So
yeah, thanks.
Something to that.
I think the natural estimation for the opponent is pretty useful. So sorry, lastly, I just want to say thanks, of course, to the organizers. It's a really well done competition, and I really hope that we'll get it back next year. I'd be really excited. And I want to thank some of my mentors, Stephen, Professor Roy Fox, and JB Lanier for their advice, mentorship, and support. And that's all I had. Hopefully I didn't go too much over time. Thanks for listening to my talk.
Yeah,
Thank
thanks.
you.
Thanks, Kevin. I could relate to a ton of what you were saying, actually, as you kind of noted from some of the slides I started with. But yeah, my bot, by the way, is Marmot, but it's also, I set out to do a counterfactual regret minimization, and that is what it does. But yeah, I ended up having to make all sorts of assumptions to get any kind of practical, performance out of it. In short, and I also have my terminal. I have to say it's not as cool as yours, but my terminal does look very similar to yours, where I have all these ASCII chessboards that look exactly like yours. Where I don't know if you used a library. I just coded mine by hand, but I had they were identical. Yeah. So does anyway. Sorry, I had to relate for a second. Does anyone have any questions for Kevin?
I guess I was curious exactly what you meant by like a sub game in this case. I was sort of interested in that part.
Yeah, so so I think yeah, Ryan touched on it a little bit. So would you be familiar with like what a subgame would be in a perfect information game like chess? Yeah. Okay, so yeah, so it's more complicated in imperfect information game because it's not just it doesn't we don't know what state we're in, so it kind of has to include all states that we think we could be in, as well as for the usual definition of a subgame, it should also include all states that we know that our opponent thinks that they could be in, as well as all states that we know that our opponent thinks that we think we could be in, and so on. So kind of another way to think of it is like a public state. So yeah, it's those would be the root states of the subgame, and then just like in a perfect information game, the subgame just goes to the end. Yeah, unless it's a depth limited subgame where it cuts off after some number of moves. Yeah, does that make sense? Kind of.
Yeah, definitely. Well, it's definitely very interesting. You did a great job.
Thanks.
It feels very surprising to me how well your bot plays, given that it only searches 3 actions deep. Did you try deeper?
Yes. I think it just took too long. I think I tried one more move, but it was just taking too long, and I got better performance by cutting it down to 3. Yeah. I guess one thing that so when it actually makes a move, so when the bot actually makes a move and it's evaluating the moves, it uses Stockfish. But I think I read that Strangefish uses a 0 depth Stockfish evaluation, but I actually just did Stockfish with like a time limit of like 0.003 milliseconds or seconds or something. And so that Stockfish evaluation does do search to like sometimes like pretty deep. So I don't know, maybe that kind of covers for it a little bit.
So Kevin, when you're running counterfactual regret minimization from the opponent's perspective, were you saying, do you assume that they know your state?
Yeah.
Okay.
Yeah. That's a pretty important detail. I probably should have put that in there. So thanks for asking that.
Anyway, this is really cool. I like how they're this is one of there's a number of avenues of different bots that interest me a lot, and this is one of the ones I think is really neat.
Yeah, I really like the diversity that we have here.
Does anyone have any other questions for Kevin before we move to the last presentation? Okay, so last, Gino is going to talk about Strangefish 2.
Okay. Right, so now it's my turn to go over my algorithm. My bot was Strangefish 2, came in second place. It is, as the name suggests, a continuation of the 2019 winner, Strangefish. And this presentation, even more so than when I wrote it, given what we've heard so far today, is going to be a presentation of a sensing strategy. And because there's, the room is full of other bot authors, I'll make sure to go over some of the practical implementation details. But the important theory here, both for my own bot's performance, but also where I think it differs from what we've heard today, is in the sensing strategy. So at a glance, Strangefish 2 is a multi-hypothesis tracking bot. In the 2019 tournament, there was, we heard a couple of alternatives. There was maybe not a consensus that multi-hypothesis tracking was even viable for full games against high-level opponents. But it seems that it is. And so in this year's competition, it appears most people have converged on this exhaustive tracking of at least the arrangements of possible states. Now, the full game state, as we've discussed a couple of times, it does include not only where you've sensed, but where your opponent has sensed and what they might know. And we only heard from one player today who's brave enough to incorporate that. Eventually, I think algorithms in this game will do so, but at the moment, most of us are here at this level of tracking just where the pieces are on the board. Strangefish 2 does that. The sensing and move choices are both based on the expected value of the board state that'll be reached at the end of the current turn. And as was just discussed in the question and answer, of course, the evaluation of that board state is played out through a search in a traditional chess engine. In this case, board states are evaluated using Stockfish and augmented with a considerable number of uncertainty-related heuristics. The original Strangefish code won the 2019 Reconnaissance Blind Chess Tournament. That was co-authored by myself and my brother, Robert. And there are a couple of significant changes that I have made to update to Strangefish 2. And largely this was done as a search for improving the efficiency of the code. We ran in 2019 on a 64-core cloud instance and didn't have the capability to keep that up indefinitely. But in order to keep the code available to play and learn and test against, I started looking for ways to run it more efficiently so that it could run indefinitely on what was available to me, a 6-core cloud instance. And it has been running on that 6 cores, including 4 simultaneous games, ever since the 2019 tournament. And performance has been incrementally improving as I find some small and some very big ways that we were wasting effort that I could iron out. But in doing so, in searching through all the code for this efficiency gains, I noted that the sensing strategy, the objective being optimized, didn't match quite with what we would say in just an English sentence was what we were going for. And so in fixing that, in changing that objective, we've come up with an entirely new sensing strategy. And I think that was key to the substantial boost in performance of Strangefish 2 over Strangefish. Additionally, we found it pretty important to start adjusting for known opponents. There just wasn't a configuration or a strategy that worked against everybody. And so I don't have an individual strategy for every opponent, but after seeing some particular opponent name enough times, they will get binned into naive, average, or expert. And the configuration loaded when playing a game against them is different depending on which is the case. To help orient us, we can think the way the bot does for the remainder of this discussion. I'll highlight that every turn of Reconnaissance Blind Chess has kind of 5 steps. You learn what happened on your opponent's turn, make a choice for sensing, you receive the observation in that sense location, make a choice for requesting a move, and you receive the information about what move occurred as a result of that request. And the decision making is kind of more intuitive from the sense of, from the later decision, moving. So I'll start there. And it's simply that we look from the second to last node in the turn through to beyond the last node and calculate the expected value that would be reached based on the request we make. And in this case, it's simply using that Stockfish plus heuristic value function to give a score to every combination, every pair of move we might request and board that might be true. And the expected value used to combine those here is a weighted average, where the weights are proportional to a function of the advantage from our opponent's point of view, calculated using the same heuristics. And that doesn't account for kind of, as discussed before, propagating the probabilities over sequential moves. It's just currently, if a board is stronger for the opponent, we consider it more likely that the opponent played to reach that. Now, it's not as obvious what an analogous sensing decision might be. And so for comparison, I'll start with just a baseline. We've seen that many of the agents in the tournament use just a minimization of quantity of uncertainty. And this could be done just by looking ahead from the sense choice to the end of the following sense result node and sensing where either information entropy is highest or the expected resulting set size, and that's the sum of the probabilities for each of the observations that we saw in a previous presentation. Or a slight variation of that, you could minimize the worst case resulting set size to keep the worst case uncertainty manageable. Any of that is a viable strategy, but doesn't couple the sensing to the moving strategy. And so in 2019, the Strangefish agent used a version of sensing that I'll refer to here as information-based. And what that means is we, before sensing, calculated all of those move scores for all the pairs of moves and boards, and then looked at how the sense observations might partition and change those move scores. We sensed where the average change in those scores was greatest. And the idea there is that most significantly affects our strategic information, not just the total quantity, but the quality, let's say. But really that spends a lot of its objective function focusing on moves that we aren't currently considering. And so you may overlook information critical to what you are about to do, which is choose the following move, because you need to know the relative value of some alternative move. And so we could go entirely the opposite end and do a decision-based sensing strategy, and not only look at the move scores after sensing, but then make a decision about what move your agent would pick, and then rewind to the choice of sense and choose the sense that leads to the greatest uncertainty in your own following decision. And that again would be kind of an information entropy, but over your own following move choice. And that has some advantages, but also has some major blind spots. And so where we settled was this last option, the outcome-based sensing. And so now we're looking from this choice of sense node all the way to the end of the turn and saying not only what might we observe as a sense result, but then what would those scores be given the new limited board set? What move would we pick, and what would we expect the actual outcome to be in that case? And the maximum of that outcome is just the path down this truncated game tree that leads us to the best state. It's a little bit too optimistic in practice. So Strangefish 2 uses a lower confidence bound on this expected outcome. That is the weighted average minus 1 standard deviation. And we also find that there is some merit to these other strategies. So in fact, that strategic value of moves we aren't currently considering comes into play later, right? We're going to need that information. So the hybrid objective used for sensing in Strangefish 2 actually does include a smaller factor of the original information-based sensing score. And in addition, to keep the number of board states down just for computational expense, we also use in the hybrid sensing objective a reduced factor of just the total expected set size. And in cases where the set size has grown significantly on hundreds of thousands, we save a ton of computational expense and don't even calculate the first two, because the hybrid objective will be dominated by the third term. And now, focusing specifically on maximization of the expected outcome, you can sort of see if you look at this long enough that this is just tree search. This is a depth limited tree search algorithm where Strangefish 2 always sets the depth to be the end of the current turn. So why not look further? We should, in a sense, do better if the depth of the search is increased. And we find that's absolutely not the case. And the reason for that is the values of the decisions we're going to make on this turn end up corrupted by a misrepresentative distribution of what might happen on later turns. Right? We basically don't have a good way of predicting what the opponent is going to do in any distribution that ends up leading to a good strategy on this turn for us. And it's worth noting that we also don't have a real distribution for the sense results or the move results here in blue, but we find that the distribution that we estimate over those does produce a good strategy for the green nodes here that are our own choices, where jumping across the result of the opponent's turn any number of times ends up corrupting the values we use to make these decisions. And I think computing better values for that distribution is kind of the area of research. What might my opponent do in order to get that? What might they know? Some practical details. We use a simple time management scheme allocating a fixed fraction of the remaining time per turn. Most of that goes to sensing, and that's because the bulk of the computation time in Strangefish 2 is spent calculating the scores for this move on that board. Because so much time is spent on that, those values are cached for reuse, and as much as possible are computed on the opponent's turn, so long as they're giving us the time to do so. When necessary, the boards that are used for evaluation are downsampled, and we have a prioritization system where we always sample first the boards that are already in the cache, followed by any that have information regarding check, and then if quantity is still available, we start sampling from the remainder of the boards. That is kind of the blitz through Strangefish 2. I know I didn't cover the heuristic value function itself, but really the core to this is that sensing strategy, but most explicitly coupling sensing to the expected outcome after your own move was a major performance boost. And I think something that a lot of the strategies can consider incorporating. Thank you all. Any questions on this?
Was that change in sensing the change that was incorporated into version 165?
No, good question. That I can trace back to exactly when that was put in, because that history of Elo on the server is a little bit corrupted, because Strangefish 2 was actually the account we used to dummy test our server communications back in the original tournament. So a lot of the early versions are just intentionally garbage. But at least the last 100 versions are this, playing with different configurations, time management, efficiency. There were some bugs. 165 might be the time I ironed out. We do some refinement on, I don't check all, obviously, 64 squares when sensing, because we know intuitively that sensing on the border is suboptimal. But it's also pretty trivial to check which other squares are suboptimal in any given state if you have the full set of possibilities. You treat the sensing as a partitioning of the current set of boards into subsets where each of those blocks adds up to the current set and corresponds to which observation you might make. And you can look into refinement of set partitions to look for a function that tests whether a partition is finer than another partition. And in the case that is the coarser partition in this is just never strategically viable. And so we've got an efficiency boost from calculating that. But some of the substantial jump later after the important sensing change was made was just finding out that test was implemented incorrectly. So some of it is theoretical gain in the kind of generalizable strategic sense, and some of it is just bug fixing. I am happy to keep taking questions, but I also want to encourage just general discussion on reconnaissance blind chess on this tournament. I think a lot of the value in getting together like this for a conference is kind of the conversations that would have happened in the hallways. And since we won't have that opportunity, please do permit yourself for more speculative discussion, revisit other presentations if you had questions still burning on those. But just wanted to make sure you all know the floor is open for that.
Did anyone have any other questions for Eitan? I know I moved that one along, which I felt a little bad about.
Yeah, I just wanted to clarify something, and I think Kevin also did something kind of like this. I just wanted to double check that in trying to represent what your opponent was doing, you basically played yourself. Is that correct?
Yeah.
Okay.
Yeah, I was treating they were making moves the same way I would, with a caveat that we were using, like, we were able to look one turn further because we were only doing like second degree knowledge, if this is what it's called. Like, we were able to incorporate where they would have moved into our turn, whereas they couldn't have moved, like, incorporated where we would have moved in response into their move. But for the most part, it was the same.
Did you do any, because this is something that I struggled with in trying something like that and having it not work. Did you do any testing on how plausible that kind of representation ends up being empirically?
Plausible in terms of, like, computation, like tractability, or what do you mean?
When you're making these kinds of, so you're using hypothetical play against yourself as an opponent to make your own decisions. The hypothetical future is you playing against you, right? How often, for example, are the moves made by you what the actual opponent moved?
Yeah, that's a good question. I think, like, for some opponents it worked really well. And, like, there is a consistently, like, small number of board states. And then for other opponents, it was disastrous, and the number of states would explode. Like, you can't use that to model, like, a random opponent, for instance. Like, it's just not feasible. So, like, one thing that I tried incorporating was using sort of, like, setting, like, profiles for, like, how the different opponents would play. So specifically, like, because I was doing, I was looking at how long, or I was looking at, like, moving once and then getting to move a second time. So and then sort of doing a weighted average of those two scores. So certain opponents, I would weight the second move much more than others. So for example, I was pretty confident Oracle wasn't using, like, taking any risks at all, so I wouldn't weight it at all, and that helped a little bit. But in general, yeah, it's not a great way to keep the number of states down.
Interesting. And Kevin, I think if I remember correctly, you did something kind of like that as well.
I think it was a little different. So I don't, like, apply the same algorithm to my opponent and myself. It's so for predicting the opponent's moves, I do that CFR. So I kind of predict, or think, oh, they're gonna sort of play a Nash, and then for my own move, I just kind of pick some best response against that. So it's, maybe you can think of it as kind of the opponent prediction as being in the driver's seat of the algorithm, and then the best response computation is just just follows naturally from that, or I guess the sensing comes first and then the action comes after that. But yeah, it's two different agents, I guess.
Got it. And Greg, as for your as for your comment. I'll look at that. Thank you.
There's actually one thing that I was interested in with Strange Fish 2, and it was something that Ganesh sort of touched on as well. Sort of the idea of changing strategies in response to different bots. So like Ganesh talked about potentially changing to a bot like an endgame bot or an attacker bot. So I was wondering how Strange Fish 2 managed like the sorting aspect of sorting bots into naive, average, and expert, and if there were any other potential like categorizations or methods that you're interested in using to make bots that are adaptable to different strategies.
Yeah, I think that's a great question. I've been pretty resistant to doing that over the development of my bot because I wanted the algorithm to be kind of generalizable, and I'm not sure I have maybe a really sound explanation for why I feel like taking advantage of knowing who your opponent is somehow easier. But you do know that, and you probably should use that information. And so I think doing so kind of automatically or characterizing your opponent based on the decisions they may have made is a really good way of being able to apply that sort of categories, that sort of strategy adjustment kind of on the fly to new opponents. And even in that case, you'd be able to do it if you didn't have your opponent's name. You'd sort of observe what they did and respond appropriately. At the moment, though, this is done after the fact, just using game replays. And it's simply a matter of many hyperparameters in Strange Fish 2 having vaguely intuitive effects on the overall strategy. One of the more obvious ones is that weighting over the boards as a temperature parameter. So whether it's mostly a uniform distribution or very heavily biased towards strong positions, then the distribution is better reflects what your opponent actually does if you put that if you adjust that distribution based on who you're playing against. And so I have the ability to kind of drop usernames into these categories and could create an arbitrary number of categories. And if I felt I had the time or interest to fine tune these hyperparameters for against specific opponents, I'm not going to do that, but it could be done. What that kind of extends to, you alluded to some of the end game bot and so on. I do have adjustments to those hyperparameters mid-game. And that permits things like, oh, I'm running out of time. Doesn't matter if this strategy is generally a little bit weaker, I'm going to run out of time, I have to play aggressively. And so I just start, every turn that number goes, put the opponent in check, put the opponent in check right now. Just keep increasing those numbers. And so there's a maybe boundless opportunity for saying, in this particular circumstance, I should make these adjustments to the strategy. At the moment, I don't have that. And I do think we've referenced the bitter lesson previously. I think if you were going to go that route for endless fine adjustments, you'd want it to be learned. You'd want the agent to be in control of that itself. I don't feel that I am good enough at this game as a human player to even know what to be adjusting. I still lose to my own bot. So until that's not the case, I'm going to let it make the decisions.
That's great.
Thanks for the question.
To be clear, though, are you saying that the selection of who goes in what bucket is a handcrafted
manual yes.
decision? Okay.
Yeah.
So that's like potentially a place where you could apply like an agent that would sort different and different strategies.
Yeah. So if I changed the actual bot using the account named attacker to be Fianchetto, I would lose even more to it. Maybe that's a bad example. I already lose to Fianchetto, but you could pose as a known opponent name, and because I don't adjust until after the game is done to a username or an updated strategy, it is certainly exploitable. And I think that exploitability is sort of what I want to avoid by incorporating opponent names, but at the moment, we've sort of acknowledged that everyone who's not going for a Nash equilibrium strategy is exploitable, and the state of the art for this game is still exploitable strategies that mostly manage their own uncertainty. And I really look forward to incrementally pushing on that boundary and getting towards strategies that model their opponent's uncertainty and aren't exploitable. But I'm not there, and I don't think that any of the other bots are really getting into that area yet.
Any other questions or comments from anyone?
I have a question I just want to kind of open for discussion here. One of the things that happens in a lot of popular human played games is we compare these agents to human players. You know, where are we relative to the strength of the human mind and expert play? And this game, you know, was made for this research, so it doesn't have quite as many human players. We don't really know what the upper limit is on human play, but have you all played against your bots or other bots as human players, and where do you find that these agents are compared to your own abilities, or where do they agree or differ from the way that you think about the game?
I'll chime in and say that I played 100 games rated on the server on purpose just to get an estimate of an answer for this, and I'm apparently weaker than my bot.
Me too.
Your question got me thinking. I was wondering, actually a little while ago. So obviously there's been this whole movement in the chess world. It's become a lot more mainstream since COVID and with the Queen's Gambit and everything. Has there been any talk about maybe trying to get this more into the hands of chess streamers and the young grandmasters on Twitch? I could see them loving this kind of thing, and I'm wondering if there's been any thought about that.
There has been talk about that. I would really love to see that. It's a little out of my wheelhouse to know how to make that happen, but we are certainly looking into it.
Yeah, I'll just add, it is something we're trying to do the extent we can, but yeah, both Gino and I, and in general, you know, the applied physics lab is a bunch of scientists. But you know, I guess one of our ways of attempting to do this was to add the mobile app. That's kind of an example, but I guess for the most part, our approach at this point is to just try to do things like this and just get more people. You know, it's probably one of those things that as we reach critical mass, more and more people will play, and there'll be growing human interest. And along those lines, one thing we would like, and if anyone, this is also an open question, but you know, one thing that's really nice about chess and poker is people play these enough that you have really nice baselines from, you know, human professionals, and that's something we don't have here, but it'd be nice. And so I guess part of my open question is, what would you know, in the absence of that, can you imagine a sort of wow, someone really crushed this game, you know, because typically that has been, we've exceeded, you know, the top human in the world, is frequently the benchmark.
So when will we know we're done?
Yeah.
Good question.
So similarly, if anyone has suggestions on ways you think we could, you know, get this in front of grandmasters, or however it was phrased, we'd certainly be open to the suggestions. I mean, we also.
So I was just gonna say, you know, one of the rivals, the other blind chess, the dark chess, got added to chess.com, and that really helped it take off in popularity. And,
okay.
I think I did see a lot of streamers playing dark chess about a year ago, or half a year ago.
We had talked about using Lee chess to I don't know. Does anyone have thoughts? Is chess.com the right place to focus, or is Lee Chess?
Well, I think
or-
Lee Chess would be a good opportunity since there's already dark chess on chess.com.
Oh,
You
okay.
could add your version of Lee Chess, and Lee Chess is better. It's open source and free, whereas chess.com is like a company, I think. So that yeah, I think that could be one potential avenue.
Yeah. Thanks.
Especially since it's open source, it could be easier, not easy, but.
And then the other thing that Gino and I have to figure out is just finding the time and to do it.
Yeah, we all should work on this a little bit more. I have one last question. I think this is the right audience for. I'll just stay up front. I'm generally against all rule changes to RBC. I think it should be researched in the state that it's in, and that we have lots of research left to do before we play with making it any harder than it is. But we've had some more skilled at traditional chess than I am players point out that it might be better for human players with incremental time control. And so in addition to the 15-minute clock, you'd get something like 5 or 10 seconds added per turn. The only problem with doing that, the only reason we haven't just automatically done that already is then there's no guarantee that the games are finite, as there would be in traditional chess and as there is with a limited clock. And so the corresponding rule change, if we do add incremental time control to make the game better for human players, would be maybe just a number, a finite number of turns, a turn limit, 100 turns or 120 turns or something like that. Does anybody feel that that would greatly change the game? Should we avoid making that change, or should we encourage making that change?
You could borrow the rule from chess about only a 50 move limit if you don't move any pawns, but then moving a pawn resets it.
Yeah, we've thought about that. You may not know if your opponent moved a pawn, and I'm not sure if that makes that more or less interesting as a rule, but.
Right, good point.
Yeah, I've been thinking about those draw rules, and I see no reason not to, like, even independent of the increment thing. I think the game would be improved if the 50 moves draw rule was implemented, because I don't know, like even without the increment, there's a lot of end games where it's like king versus king, or at least I've seen a couple, and then it's just like, oh, can you spam moves faster than your opponent?
Yeah, it comes down to computational speed.
Yeah, so there, I think that some sort of, I think, yeah, there's no, we can re-implement like a draw rule or something.
I would like to see more draws reflected in the games between the top bots, because I think a lot of them are coming down to what could be a draw otherwise. So it's fair.
Would you think for this game say a 200 move limit or something? I don't know. I'm imagining 50 for some of the games might be shorter than what we want. Or do people think 50 is still the right number?
Well, that's only without pawn moves. So the actual number of moves may be quite a lot greater than that.
Oh, I see. Okay.
But only in cases when those moves are interesting. So, 4,000 turns of none back, no move back and forth won't happen anymore.
Okay. Yeah, I guess I was eliminating that because I was personally not a fan of, well, I guess maybe we weren't going to reveal this, but anyway, I hadn't worked through how we were going to. I like the idea of not revealing when someone has made a pawn move.
We wouldn't reveal it. It would be part of the state you're tracking, just like castling rights. You don't explicitly know that your opponent castled, but you know that if they castled, then they have.
And so you just don't know when you would draw. It just, yeah.
Yeah,
you
know that there's a possibility this move will draw.
Yeah. Mm-hmm. Yeah, that makes sense. There's no reason you need.
I appreciate the discussion on that. I think improving the game for human players and adding draws is like the correct tiny change that the game might need. Well, we have used up just about all the time we signed you all up for. So any last comments we want on the record before we close up and go back to?
All right, I do have one discussion question that
Please.
has been on my mind for a long time. So I'd be remiss if I didn't ask it. Okay, the question is this: what do you all think in an equilibrium? How well would attacker bot do against equilibrium strategies? Do you think that attacker bot would always have a win rate of 0? Or do you think that for any equilibrium strategy you play, it would lose sometimes to attacker bot?
Mainly, I
A
think
lot of it.
you go ahead.
A lot of attacker bots wins come from timing out the opponent, but I think if we're talking about equilibrium strategies, then that's irrelevant.
Yeah, I guess for Penumbra, you probably never lose to attacker bot because you know exactly what it's going to do. But
I think I have hard coded. Like it doesn't even use the neural network right now against
Nice.
Okay, yeah.
attacker bot. I should have mentioned that.
Yeah,
I'll say I think attacker bot may not win games. A very aggressive strategy that continues moving after the first attempt fails probably would win a considerable number of games. I'll point to the recent Kaggle competition. It was really a test for their competition platform, but they ran rock, paper, scissors with no rule changes. It was just regular rock, paper, scissors. And the really kind of interesting point made was optimal strategies didn't win, right? They can't win. They're going to break even all the time. And the winner is the strategy who best exploits the other people who are trying to exploit the people who are, and so maybe an equilibrium strategy isn't actually going to be the one who comes out on top of a field of opponents, attacker included. No, a little hard to say, but I tend to maybe undervalue equilibrium strategies, particularly in fixed tournaments like this.
Is Fianchetto hard coded against AttackBot? Or like are all the ones we submitted to the competition hard coded, or?
That's actually really coincidental because we actually didn't hard code anything for attacker bot specifically, but we were actually thinking of doing that like 2 days before the competition because we were losing against like some games against attacker bot, and specifically it loses out a lot of rating, right? Since attacker bot is low rated.
Yeah.
But yeah, I think some of the adjustments related to the hyperparameters and score related constants did in fact in the end made it possible for us to not hard code it. But yeah, I mean, like in terms of modifying those constants, they were really arbitrary, and it just was very coincidental that it in fact happened in the end.
Well, thanks to everyone who presented and joined in on the discussion. I think this is a great way to conclude the tournament and kind of learn from each other's experiences. I hope everyone continues to the limits of their availability to develop for Reconnaissance Flying Chess. You can always send feedback or suggestions through our email or the Reddit page. I look forward to more games.
Thank you, everybody. Hope it was fun and you learned.
Thank you so much. Hope you all have a nice day.
Thank you.
Thanks. I'm gonna go get some sleep now.
Yeah, good night, depending on your time zone.